So today we're going to try to answer the question, what is the factorial of negative 1/2? Seems like kind of a silly question at first, because if you're familiar with the factorial function, it's defined for integers like so. So some integer n is defined to be itself times itself minus 1 times itself minus 2, dot dot dot, all the way down to 1. So, for example, 3 factorial would be 3 times 2 times 1, and then you stop, which would be 6. But how are we going to do this for, first of all, fractions, like a half, non-integer numbers, because as we go down this path, we're not going to end up at 1. So how are we going to know where to stop? And also, how do we do this with negative numbers? Because this would just continue on to get more and more negative. So we're going to try to answer this question today. So to start off, we're going to introduce something that will actually generalize the factorial function for all real numbers, so not just integers. And that function is called the gamma function. Gamma function. And it is defined like so. So gamma is a function of, let's say, t. It's defined to be the integral from 0 to infinity of x to the t minus 1 times e to the minus x dx. So note the actual gamma function is a function of the variable t, but the integral that it is defined to be is over the variable x. Now, how, you might ask, is this the same or related to the factorial function? Well, I'm going to demonstrate that by solving this integral, and what we're going to do is integration by parts. Now, the way I like to think about integration by parts is the following. So to set it up, if we're taking the differential of the product of two functions u and v, by the chain rule, it gives us, or the product rule, sorry, gives us u dv plus v du. And then if we take integrals of both sides, like so, and rearrange, we'll get integral of u dv equals, then this term, the integral cancels out the differential, and you get uv evaluated from whatever your limits are, minus integral v du. So this right here is integration by parts. So our job is now to assign one of these terms to be u and one of these terms to be dv. So let's start up here with our gamma function. And we're going to let u equal x to the t minus 1. And we're going to let dv be e to the minus x dx. So then, if we take the derivative of u with respect to t, du dt, and du will be t minus 1 times x to the t minus 2 dt. So we just took the derivative du dt and we brought the dt over to the other side. And then dv, we see that dv dx would be e to the minus x right here. So if we integrate both sides, we get v is minus e to the minus x. So now that we have that, we see that we let this be u and this be dv. Then using our product rule, or our integration by parts, there should be a u. We see that the gamma function should be equal to u times v, so we do u, which is xt minus 1, times v, which is minus e to the minus x. And we're going to evaluate that at our limits of integration, which in our case are 0 to infinity, minus the integral of v du. So we plug in v minus e to the minus x, and then du, which is t minus 1 x to the t minus 2. Sorry, kind of running out of room there with dt there. Alright, so let's solve this. Alright, so we can take this, and all I'm going to do is have these two minus signs cancel each other out and bring out the t minus 1, and this is our gamma function here. So I want to look first just at this first term. So just looking at this first term, let's evaluate it. Alright, so evaluating it, we get the limit as x goes to infinity of minus x t minus 1 over e to the x, minus the limit as x goes to 0 of minus x t minus 1 e to the minus x. Alright, now obviously this term here goes to 0, because when x is 0, this is 0, so 0 to anything is still 0, and times anything is still 0, so this whole term just goes to 0. Now what about this term here? Well, we're going to use something called L'Hopital's rule. So taking a look at this term on the next screen, where I just pulled out the minus sign, we see that as x goes to infinity, this numerator goes to infinity, but the denominator also goes to infinity. So we can use L'Hopital's rule. Now what does L'Hopital's rule say? That says that if we're taking a limit where both the numerator and the denominator go to infinity, then it's the same as taking the limit where you differentiate the numerator and you differentiate the denominator. And you can do this as many times as you want. So notice if we take derivatives with respect to, let's see, x, then the denominator is going to just stay e to the x, because the derivative of e to the x is just e to the x. Now when we take, here's the interesting part, when we take derivatives of the numerator, it's going to go down slowly, and here's what I mean. So if we have x t minus 1, if we take one derivative with respect to x, it's going to give us t minus 1 times x to the t minus 2. If we take another derivative, we'll get t minus 1 times t minus 2, x to the t minus 3. And eventually, we'll get it down to t minus 1, t minus 2, dot, 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 dot. Eventually, one of these terms is going to be x to the t minus t, because this number keeps growing until it hits t, but that's clearly just 1. So, if we take the derivative of the numerator, t minus 1 times, with respect to x, and we take the derivative of the denominator, t minus 1 times, with respect to x, we will get that this limit gives us remember, by L'Hopital, we can take, so taking these derivatives, t minus 1, t minus 2, dot, 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 all the way eventually we'll hit the number 1. And down here, this just stays e to the x. So now we see that as long as t is a finite number, this numerator is finite, but this denominator is going to go up to infinity. So this whole term is going to go to 0. So if we look back here, this term also goes to 0. So both of these go to 0, so that means this entire term goes to 0, and our gamma function is just equal to this. So let's rewrite that. We have that the gamma function equals t minus 1 integral 0 to infinity of x to the t minus 2 e to the minus x dx. And we got this from integration by parts. Now, what do you notice about this right here? This is very similar to our definition of the gamma function, except this term is different. But note that t minus 2 is just equal to t minus 1 minus 1. So this whole thing says that the gamma function of t is equal to t minus 1 times the gamma function of t minus 1. For if you recall our definition of the gamma function, if you just plugged in t minus 1 there, this would become t minus 2. So now we have this recursion relationship that looks eerily similar to the factorial function. Because here's our recursion relationship for the gamma function. We know for factorials we have this definition. Wow. So there's the beauty and magic of the gamma function. It actually gives you the same, it's actually a generalization of the factorial. Oh, sorry, not quite. This is a very important step. Sorry, that is what the factorial function is. So we see gamma it has a similar relationship to the factorial function, but it doesn't exactly map t to n. In fact, what it does do, as we'll see, is it's going to map t to n minus 1. So let's look at that. If we have gamma of t gives us t minus 1 times gamma of t minus 1, then that's going to be equal to t minus 1. So if gamma of t is t minus 1 times gamma of t minus 2, then gamma of t minus 1 has to be t minus 2 times gamma of t minus 2. Right? So we can continue this on, and eventually we'll get down to t minus 1, t minus 2, all the way down to gamma of, well, t minus 1, which is going to give us 1. Now note that we can stop here, because gamma of 1 is going to be x to the 1 minus 1 times e to the minus x dx. This is just 1. And so the integral of e to the minus x from 0 to infinity is just going to be minus e to the minus x from 0 to infinity, which is going to give us e to the minus 0 minus e to the minus infinity. This goes to 0, this goes to 1. Aha, and it turns out that this is 1. So gamma of t is t minus 1, t minus 2, 1. But what is that equal to? Well, that's just t minus 1 factorial. So there, even though we messed up earlier, this we actually see the gamma function of t is equal to the factorial of t minus 1. So, now armed with that knowledge, which I will rewrite up here because it's so important, gamma of t is equal to t minus 1 factorial. But now, t does not just have to be an integer. So, we are now able to try to answer our question. What is negative 1/2 factorial? Well, let's see. We know that we need it in this form. So we say, well, negative 1/2 is equal to 1 minus 1/2 factorial, or negative 1/2 factorial is equal to 1 minus 1/2 factorial. And now we see that in our case, t is just 1. So this must be equal to, sorry, negative 1/2 factorial is equal to 1/2 minus 1 factorial. Right, a half minus 1 is negative a half. So now we see from over here that t is equal to 1/2. So this is equal to gamma of 1/2. Aha! So now we can answer the question of what is the factorial of negative 1/2? Well, it's going to be whatever happens when we plug 1/2 into our gamma function. So let's see, this is going to be integral 0 to infinity x to the, remember it's t minus 1, and in our case t equals 1/2. So a half minus 1 gives you minus 1/2 e to the minus x dx. So there we go. All we need to do now is solve this integral, and that will give us what the factorial of negative 1/2 is. So, how do we solve this? We're actually going to do a u substitution because it will help us greatly. So we're going to let u equal x to the 1/2, which would imply that du, so taking the derivative with respect to x, du dx, would give us 1/2 x to the minus 1/2 dx. Alright, so replacing all this stuff in terms of x gives us that x is u squared, and let's see, that dx is going to be 2 x to the 1/2 du, but x to the 1/2 is just u, so this is equal to 2u du. So we're going to plug this stuff all up into this integral. So this integral now equals integral, let's see, we're going to replace, let's see here, we're going to say that x equals u squared, so we have u squared to the minus 1/2, e to the minus, now x is equal to u squared, and then plugging in dx, 2u du. Now these 2's cancel, and this is u to the minus 1, and this is u, so the u cancels with the 1 over u, and it turns out that our integral is just equal to 2 e to the minus u squared du. Now I've left off the limits of integration just for a second, because whenever you change variables, you got to make sure that your limits stay the same. So let's see. When x is 0, u is 0, yes, and as x goes to infinity, u also goes to infinity. So we can keep our limits the same, 0 to infinity. Turns out all we have to do to find the factorial of negative 1/2 is solve this integral. So let's do that. We know that, or we know now, that we want to figure, so let's do that. We know that we want to figure out the factorial of negative 1/2, and that is equal to our integral here. Now, remember, it was equal to 2 times the integral 0 to infinity e to the minus u squared du. Now note, this is an even function because it's u squared. So if we plug in a positive value, it's positive, and if we plug in a negative value, it's still positive. So since it's an even function, it's symmetric about 0. So whatever the integral of this from 0 to infinity is, will also be the integral of this from negative infinity to 0, because it's symmetric. So if you plug in a positive number, or if you plug in the negative t, then it's the same as plugging in t. So when we say that this is twice what happens when you integrate over all positive space, then we can just write that as the integral from negative infinity to infinity of e to the minus u squared du. Because this is saying, look, this is just from 0 to infinity. And we know that whatever the integral from there to there is, it must be equal to the integral from 0 to minus infinity. So if we're doubling what this equals, but this equals that, then we can just do the integral of the whole thing. Now, it will make that. Now, how do we solve something like this? Now, this is called the Gaussian integral, and I will show you to solve it. It's very neat. And one trick is that we're going to square everything. All right. So we're actually going to look at what the square of this is. Now, we're just going to use some dummy variables because we're going to square this, and squaring it means that you can write it twice. So let's get this out of the way. But we can just write it with two different variables because, again, u is just a dummy variable. So this is the same as the integral from negative infinity to infinity. Let's use x for the first one. But now, remember, squaring means times itself. But now we're going to use y instead. So, combining these two, we get double integral of e to the minus x squared plus y squared dx dy. Now, from here on, here's the genius of why we wrote it like this. We're going to convert this to polar coordinates. So if we're going from, take a look at a graph here, x and y. If we're going from negative infinity of x to positive infinity, right, from minus infinity to infinity in the x domain, and positive and minus infinity to positive infinity in the y domain, we're going to end up covering all space. So now I want to convert to polar coordinates. So that means you go out some distance r and over some distance, some angle theta. And we still want to cover up all space. So it turns out that we're going to want our r to go from 0 to out to infinity, and we need our angle to go all the way around 0 to 2 pi. So we can convert to polar coordinates. So we're going to go 0 to 2 pi for theta and 0 to infinity for r. Now, how do we do this? Well, we know in polar coordinates that x squared plus y squared is equal to r squared. So we're going to have e to the minus r squared. And then we know that the area element, in Cartesian it's dx dy, but the area element in polar is dr d theta with an extra r. And you can see that on a graph. If we want a tiny little sliver, we have r here, and then times a differential little angle d theta. That r d theta is going to give us this arc length, and then we do a little dr just to push it out a little bit, and you see that we have our differential area element in polar coordinates. But there's also, you can get it from the Jacobian, and you can look up about exactly how to do that. So here we go. All in all, we have that -1/2 factorial squared is equal to that integral right here. So first we see that our integrand doesn't depend on theta, so we can just do the theta integral. The integral of d theta from 0 to 2 pi is going to just give us 2 pi minus 0, which is 2 pi. So now we're just left with the integral from 0 to infinity of r e to the minus r squared dr. Alright, and we can do that. 2 pi. Let's see, that's just going to be minus a half e to the minus r squared from 0 to infinity. Because this is the antiderivative of that, you can check, because when you take the derivative of this, a minus 2r comes down, so the minus 2 cancels with this minus 1/2, and then there's the r, and then the derivative of that just stays the same, of the exponential stays the same, so it stays there. These 2's cancel, and I like to always say that you can take away the minus sign if you just switch the limits of integration like that. So this is going to equal pi. Now plugging in 0 to this just gives us 1, and plugging in infinity to this is e to the minus infinity. That goes to 0. So I'll write that out. That's like e to the minus 0 minus e to the minus infinity. This goes to 1. This goes to 0. So it turns out that it's just pi. So now, but that was the answer of the square of what we were looking for. So if we just take the square root of both sides, we get the astonishing result that the factorial of -1/2 is equal to the square root of pi. Wow. Now that is crazy. You know, we generalized the factorial function to work for, you know, all real numbers, and actually complex numbers too. You could put that into the gamma function, I think, for all real numbers. So it doesn't just work for integers, it works for anything that your heart desires, and it will tell you what the factorial of that number is. So, you know, not really particularly useful for anything, but just a fun little mathematical exercise that you can tell people. The factorial of a negative fraction, -1/2, is equal to the square root of pi. Well, thank you guys so much for listening. My name is Ben Hall, and I'll see you next time. Bye.